Hello. Okay, so this is going to be a version of the class that I delivered yesterday live to the classroom and the students. It's not going to be identically exactly the same because, of course, I had questions from the students coming at the time, and also because I was able to use the laptop interactively to illustrate a couple of little examples. Nothing very important. When I finish delivering the essential content, I will make an effort to see if I can actually record the screen and show a few of the same things that we did. As I said, whether I'm successful or that or not, I think you will realize as we go along that is really not essential, not very important. So first, a word or two about the course grading and so on. As you can see from the syllabus that I put 50% of the weight on regular assignments that we'll have through the semester, and 50% to a final presentation and sort of a little write-up that goes together with it. I originally thought, and I've done it in previous semesters a couple of times, to actually make the writing of an actual paper part of the final presentation, a paper that should be written with the intent of submitting it to publication, at least at some conference. But I decided against it this time around, and that does not to say that you cannot still opt to do that. But what I am requiring is simply that you turn in the day of the presentation, which would be a PowerPoint presentation of a topic that you've selected that would last perhaps 15-20 minutes, that you have a write-up that goes with it. That write-up could be, let's say 3 or 4 pages or something like that, that supports it. It is, if you would like, and you're encouraged to write something up with the view that it would be an actual paper, then, if the quality is sufficient, then I will work with you following the semester if necessary, because normally this thing happens at the end, to polish it and so on and submit it. As I mentioned before, I've done this a couple of times, and we've sent papers to the International Model Analysis Conference, and some of the students have actually managed to come along. Northeastern has provided some support, not full support, but some partial support, and we've gone to the conference, and the students have not the students, a couple of the students have presented their papers in the conference. So with regards to the topics that appear in the syllabus there, they are nothing else than what I had in mind as I was writing. They are just simple suggestions, not even strong suggestions, just ideas. You are certainly most welcome to pick whatever you might be interested in, something that you come across as the course goes on, or whatever you'd like as the topic for your final presentation. Okay, so that's more or less where it is. With regards to you guys that are in Vermont, I guess we will do those in Skype. We'll somehow set it up so that when your turn comes up, we can see your presentation in Skype. All right. There is, of course, I'll keep open one possibility, which would be, I'm not saying that this would happen, but I will keep open the possibility of perhaps, given my connection with your professor, Eric Hernandez, that I may actually go visit Eric or something like that, and if I am in Vermont, then you guys could do the presentation live for me then, if it works out at the time. But okay, so having said that, let me then begin with the description of the material that we did yesterday. I actually cut down some of the content, given the fact that we had the problem with the lecture, so that this would not be too much. So first, let's start with the idea of identification, okay? Now I'm going to stop for a second just to go to the camera and see how that is looking. Okay, it's not really dark, but it seems like you can see it. So I'll try to write as dark as possible. These are not the best markers. Now, here is some domain omega, right? Some domain omega, and this domain is subjected to some, this may be not too bad, let's say u of t, and has some y of t. So these are inputs and these are outputs, right? So we have inputs here, some sort of a domain, and some outputs on this side. Okay, let me check again to see how that brown looks. Okay, not bad. So the objective of identification, or I guess you could say when we're all said and done, what we're trying to do, or what identification does, is simply to provide us a map between inputs and outputs, right? So if when we finish, we say that we have, this is the answer, whatever form it wants to take, this is the ID result, then we've succeeded, at least in this limited description, if I am able, given an input UA, to tell you what the output YA would be. That is what my identification model is. Notice that it would make no sense to talk about what happens at a place where there were no measurements. Because let's say, for example, that our structure is this, and that we had measurements, let's say we had some inputs here, U1, U2, and let's say an output there, okay? So this is the inputs and these are the outputs. If I finish the identification, and notice that in the context of identification, we have no idea about the topology of the structure or of the system. That could be a car, could be a plane, could be a building or a bridge or something. I only need to know the signals U and the signal Y. When I finish, I have the ability to map U to Y. So given a new set of U's, which were not used to perform the identification, let's say this new U's here, okay, I should be able to say that this is the new Y. So my ID allows me to predict. It would not make any sense from an identification perspective to ask the question, what is happening on this level? Because we had no sensors over there. In fact, that level has no particular meaning, or that position, because we need not have any topological understanding or perspective of what is the structure that we're looking at. That's not to say that we might not be interested in what happens here, and we may want to use that information that we already obtained somehow, but the ID itself is concerned with the map between this input and between the inputs and the outputs, okay? Now, it may be that the structure itself, omega, is whatever, right? It is nonlinear. Now, if the structure is nonlinear, then many of the niceties that appear when we have linear systems disappear. And this ID might just be some sort of neural network or something like that that allows us to map inputs to outputs. However, if we can make the assumption that this omega is linear, okay? If we assume that omega is linear, or if that happens to be the case, then many things become possible. And by linear, what do we mean? That if UA gives YA, then 2UA would give 2YA, right? If the system is linear, not only can we get this map that we're talking about between input and output, but there may be certain characteristics of this map that are very useful and meaningful to us from a behavior perspective. Something like natural frequencies, zeros, mode shapes, damping, etc. Concepts that are really restricted to the case of, or fraction of critical damping, which are restricted to the idea of linear systems. In this class, in the very large majority, we will be concerned with the identification, well, not only, but with the identification of systems in which the assumption of linearity is acceptable. Okay? So we go on that premise. Now, I made a comment in the class yesterday that I'd like to make sure I don't forget here to mention, which is this. As you review when you read literature in structural health monitoring or in identification, at least related to civil engineering or structures, you often find commentary which is rather inapplicable, because people might often start papers with things like, you know, it is very important to know this and that for design. Anytime that you talk about design, you're not talking about identification, because identification means that you already, well, of course, in mechanical engineering you might be, because you're designing a new Mercedes-Benz or something, and you're going to build 10,000 of them, or 1,000,000 after and you're working with a prototype. But if you're talking about designing a particular structure, which is going to be one, right? If you can do ID, it's because it's already been designed and it's already been built, because there is no such thing as ID on a drawing. So identification is not, if a paragraph in a paper begins with, it's important for design and this and that, okay? Or it's important to know what the loads are, and that's why we're going to do identification of the loads. Well, this is after the fact, right? The structure must already exist in order for you to do any of these things. That's not to say, of course, that the identification is then, well, I guess I shouldn't say that's not to say. I guess the logical question then is, what is the identification good for if I can only use it after I already have the structure built and completed? Well, it can be useful for various things, right? For example, and the most obvious one, I think, it's monitoring, right? Because if we have a model, a mathematical model that we obtain from data, right, then we can examine whether that model has changed with time. And so when I say model, I don't mean a finite element model. I mean we have a system with some inputs and some outputs, and we have an ID model. And that ID model then can be interrogated as time passes. So every time we can ask the question, is the model essentially the same? If our answer is yes, whether we do it on day 1 or on day 10 or on day 1000, then we can say that from day 1 to day 1000, when we do identification, we seem to get essentially the same model, so we feel reasonably confident that nothing strange has happened and our structure is fine. Of course, monitoring can be changed to, we can ask various things, because if the answer is that something has changed, then we say, okay, the structure has suffered something, or something has happened, right, that has made the structure, this identification model change, and so we might say that damage has been detected. And so if we detect damage from identification, we may want to ask questions such as where, or how large, and so on, right? Let me see if those things are being visible. Yeah. So we might ask questions like where or how large, and so on. So these are all questions that we can get some help from the system ID. We can, in addition to that, use identification for something that is quite important, which is model updating, right? In other words, we have some sort of a system. We have a system. For that system, we have some finite element model. And again, I repeat, this must be an existing system, right? Why would you want a model of an existing system? Well, because you may be wondering what happens if, right? Let's say we use civil engineering again. I have this building, very tall building or something, and there is a plan to install some sort of a machine here that is going to operate when it's on balance and produce some sort of a load, right? And we are interested on finding what is the vibration expected in the various levels, because we've got, you know, some sensitive equipment over here, or we got some people or whatever. So we want to know what is the effect of this machine that is planning to be installed in this level. Well, the building is existing. You can say, well, that's no problem, I'll just make a model of my building and find out. But your model of your building is not going to be the building, and it might be significantly off. So your calculations might indicate that the vibration here will have an amplitude of A. When it ends up that you actually do it, it turns out to be 150% of A, for example, and then you kind of fail because that was too much, right? So model updating would be something like this. Given the fact that I have the existing building, I'm going to put some sensors on it. Let's say, you know, I'm going to measure some accelerations or something like that in some levels. And I am going to take that data and I am going to say, can I provide some properties of this building from system identification, and then contrast what those properties I got were with my finite element model. And if my finite element model does not match, and it will not for sure match what I find from the data, then I can try to kind of do something, right, to bring these two things closer together. So we refer to that process, of course, as updating the model. Now that's an art, and there's a lot to talk about, and we will actually address it at some point. But that's one application of identification with an existing structure. Another use of the same information that we're talking about that I ran into recently in a conference is, as I say, it's on load identification, as I mentioned. Load identification. Okay, so it's not because what sometimes people incorrectly write, that it is very important to know the loads in order to design something, therefore, and then the paper opens up, because again, the structure has to exist, it's already been designed. So why would you really want to know the load when you've already done it? Well, there are applications, they're not that, well, perhaps you might want to know the load because it's an application like in wind turbines, where, you know, there are many of them, and if you can identify the load on one on a certain conditions, you can sort of use that for future work on others or something like this. But another application is that I ran recently is in the case of ships that are used to break ice, for example. You know, you might have a ship that it's a, you know, an icebreaker. And so there is a lot of load coming into the hull from the breaking of the ice, which depends on the speed at which the ship is traveling, right? It may be, and this is obviously a structural issue here, loads from ice, right? And it may be of interest to you to have some sort of computations based on, for example, how much the bridge is the deck of the ship is vibrating as it moves. Perhaps you can estimate what these loads are, not the precise exact loads, but some sort of equivalent set, right? Because that information may be useful to the captain who has to decide, or who could then use the information to say, slow down or speed up or whatever it is that it's appropriate, because you want to minimize, let's say, fatigue or damage to your hull. So these are all applications of identification that are common and more or less related to structural engineering. Okay? Let's see, where did I put this eraser thing? Excuse me. to have thrown away what I was using for erasing. Oh, here it is. Okay, so in summary, we are going to operate in most instances under the premise that our system is linear. Okay. Now, because this course has a large, intimate connection, I should say, with linear algebra, right? There is some jargon that pops up. And so let's try to get it out of the way and at the same time clarify a few concepts perhaps. So first, when we say that a matrix is Hermitian, what we mean is that its complex conjugate transpose is the same as the matrix. If the matrix is real, this is the same thing as to say symmetric, right? But if it's complex, what we mean is that if the matrix is 2, 3 plus 2i, then this is 3 minus 2i, and this is 5, right? Because the complex conjugate transpose is the same as itself, right? We transpose this matrix, that means that this row becomes the column, 2, 3 plus 2i, the next one becomes the second column, right? That's transposing. And then conjugation means the 2 and the 5 stays the same. This becomes 3 plus 2i. This becomes 3 minus 2i. And so we see that these two things are the same. Therefore, we say that that matrix is Hermitian. Okay? It's obvious that, as I say, if the matrix was real, then Hermitian and symmetric are one and the same. A matrix is said to be orthonormal right? A matrix is said to be orthonormal when the matrix multiplied by a transpose is the identity. So if we have the matrix A and we multiply it times the transpose of A and we get the identity, then we say that A is orthonormal, right? That is, the transpose and the inverse are one and the same. So we can say that A to the minus